Okay, so we're in section 3.2. Last time we studied measures of central tendency. We looked at the mean, the median, the mode. We looked at something called the mid-range, which isn't particularly useful. Now we can talk about measures of dispersion, which is a fancy way of saying how the data is spread out. So let me go turn off this light real quick. So the first most immediate measure of dispersion that we're going to look at that's interesting to us is the range. The range, and you might have home on it, but basically the range is just going to be the largest data value in the set minus the smallest data. And it's really straightforward. It is exactly what it sounds like, almost not even interesting. Here, we see that the largest data value is 43, the smallest data value is 5, so the range is just 43 minus 5. That's all it is. The range is 38. That's literally the simplest thing we'll probably do all semester. And there's really not a whole lot to say about that. It just tells you how much the data values could range, how much they can go from. There's 38 possible different units, basically, actually technically 39, something like that. That's kind of what you're thinking in your mind. Yeah, nothing more to say about that. So that's kind of the uninteresting measure of dispersion. Now, the interesting measure of dispersion is something called the standard deviation. The standard deviation. The standard deviation is nice because what it will do is it will give us an idea of how much the data is spread around, and even better, if you have a symmetric bell-shaped distribution, a symmetric bell-shaped distribution, you can actually use something called the empirical rule to predict certain data values, to predict certain information about the data that you have. So a few interesting things. If you have, say, a bell curve, if you have a symmetric distribution with a mean of 10, remember for a bell curve, the mean, median, and in this case, the mode are all equal. They're all the same. And then you have a piece of data that is one standard deviation above that, is 12. Then one standard deviation below that has to be 8. Has to be the same number of units away because of symmetry. Now that doesn't sound profound at the moment, but we're going to see why that kind of matters in the larger sense, in the larger scope. So yeah, a standard deviation is just giving us like a range of values. But otherwise, it's kind of hard to describe the standard deviation. So let's do this instead. Let's define it. Let's maybe do a standard deviation calculation, except there's going to be a twist on it. There's going to be a twist on the standard deviation calculation. And you'll see what that twist is in just a moment. So basically, the larger of a standard deviation you have, the more spread out your data values are. And that's really all there is to it. So there's a couple formulas for it, but I'm just going to give you a hint right now. We're not going to compute the standard deviation straight up using the formula. Why? Because I think it's just really a pain in the butt. And so to demonstrate that, I will compute this with you guys. What it says is that, say you have a population's worth of data. So let's say that these 7 employees here represent a population. They represent a population. What you do is first you have to compute the average value. You have to compute the average. Then you take each individual data value, subtract the average, square it, add all of those up, and then divide by the size of the population. Then take the square root of that. It's kind of a nasty pain in the butt if we're being honest with ourselves. It really is. So maybe I'll show you the computation. Do we really even need to do this? I'm going to say let's skip it for the moment. But wait a minute. Wait a minute. We're going to use a calculator to do this. If you have a scientific calculator, especially if you have the TI 30X2S scientific calculator or one of similar ilk, if you have a graphing calculator, you're going to be able to compute the standard deviation, just strike directly into the calculator. You know how you do it? You put the data into the calculator. You'll literally put the data values into it. And then you will just tell it, okay, compute the standard deviation for me. So it just depends on the type of calculator you have. Now here's some good news. The good news, I have given you guys all the ability to do that. I've given you some videos, and I'll bring this up on Zoom here. You will all have the ability to use your calculator to find the standard deviation. And here's where it is. Go into your Canvas modules, look under Chapter 3 material, because we're in Chapter 3, and booyah, computing one variable statistics with the TI-83/84 calculator, which is the most common graphing calculator, or with the TI-30X2S, which is the most popular scientific calculator. If you have a different kind of calculator, if it's at least a scientific calculator, it should have its own method for computing the standard deviation. So what I would implore you to do is go to the YouTubes and search for, hey, how do I literally type your calculator model number in, say, oh, it's the TI whatever, and say computing the standard deviation or something like that, standard deviation calculation. And I promise you there's 10 nerds on YouTube who've made videos about how to do that in your calculator. So we're just gonna jump to it and use the calculator for it. Why do I feel that's okay? Well, because it's just awfully easy to make a mistake. And I think the focus of this course, there is computations, there has to be, it's a math class. But I think the ultimate focus of this course ought to be on the concepts, on the principles behind them. What does the standard deviation do? What does it really mean? Which is something we haven't really breached yet. So back to those things, back to those concepts. There's going to be two types of standard deviation. You're going to have the population standard deviation, just like you had a population mean and a sample mean. Here, you're going to have a population standard deviation and a sample standard deviation. So notice though, notice the difference. This one, the difference is very slight, but in the sample standard deviation, you're going to divide by n-1 instead of just n. The reason for this is because of, it has to do with some higher level statistical thinking concerning getting the best kind of estimator for the true standard deviation. But for the time being, we're just going to say, okay, we're almost never going to compute a population standard deviation. That's just not something we're going to do. Usually when you compute the standard deviation, you're talking about the sample standard deviation, because usually a sample is all you're going to have. And so you can go into the details of why we use n-1 instead of just n, but we're not going to get into that as well. Well, we can talk about something called degrees of freedom. This is really the driving force behind why we have to divide by n-1. Again, I'm not so worried about all that. It's a very long definition. Okay, so we have those 7 employees at the company. Now we can have a sample of 3. So let's say a random sample was taken and only 3 employees made into the sample, and those 3 employees, they had drive times to work of 5 minutes, 26 minutes, and 36 minutes. So that is the sample. So maybe we can do this computation together, and then I'll show you, I'll do it in Microsoft Excel. most likely. Here we have three employees, 3 in the sample size. So our values are 5, 26, and 36. Now the first thing we have to do is we have to compute the mean, and I'm just going to do this via the formula. We have to compute the mean of the sample x bar, so we do 5 plus 26 plus 36. And let's see, 31 plus 36 is 67. Then we need to do 67 divided by 3. And that's going to give you 22 point, and then it's 3's repeating. So let's just round to, how about 1 decimal? That works for me. So the mean then of this sample is 22.3, we're rounding. We'll just fill it into the table here. Then what we do is we take, on each of these, we take the actual data value and subtract off the mean from it. Why? Well, it's because it's part of the calculation. We're then going to square that value. So 5 minus 22.3 is actually negative 17.3. Then we need to do negative 17.3 squared. I'll use a calculator for that. Sorry, my glove. You can get 299.29. Next up, we need to do 26 minus 22.3. That's going to give you 3.7. We need to do 3.7 squared. You can get 13.69. Then you need to do 36 minus 22.3. You'll get 13.7. Then we need to square that. You'll get 187.69. Now I'm going to do something that looks bad, but I'll fix it. So you have a little more space. Now, my next step in the formula, I need to add up everything here in the right column. And I'll get 500.67. Yeah, what we did was we took each observation, subtracted the mean off from it, and so in this case it came out negative. And then we come over here, we square this value. And remember, when you square a negative number, it always becomes positive. So everything in this box here, in this column, should be positive. Now we're going to add them all up. Again, we're not actually going to ever do this calculation. This is just me kind of demonstrating it. We're going to use the calculator for this. Next, we need to do 500.67, and we need to divide by n minus 1. N was 3. So actually, we're going to be dividing it by 2. And you're going to get 250.335. And basically what I'm demonstrating is why we don't do it the hard way. It's just a pain. You divide it by n minus 1. So n was 3, so we actually divide it by 2. And then we got to take the square root of it. Again, you will never have to do this calculation. This is just kind of out of general interest. We take the square root of that, and I'll round it to 2 decimal points here. So that was nasty. That wasn't a lot of fun. And if you have a large sample size, if you have like 10 things, which isn't even that large, if you had 10 things, you have 10 different rows you're going to have here, and your calculation gets really nasty really quick. It's extremely time consuming. Yeah, absolutely. Yeah, you wouldn't want to have to do that on a test. So that's why we're going to use our other methods. So that's why I implore you to look up how to compute the standard deviation. Thing is, I can't really sit and show you how to do it because there might be 17 different calculators that different people are using. So it's best, you're on your homework, you're going to have problems about finding the standard deviation. That's going to be kind of your way of figuring out how it's going to work for your specific calculator. And that's just kind of the gosh darn truth about it. Now what I'm going to do, I'm going to use a little cheating. Give me one moment while I bring this up. We had 3 data values, 5, 26, and 36. So I'm bringing up Microsoft Excel. And here you can see we have our 3 data values, 5, 26, 36. Now you can't use Excel on an exam. So this is just me. This is one calculator you can use. Excel is basically a calculator if you want it to be. And you can do stdev.s, and that is going to be the standard deviation of a sample. You go select the data you want, and that's about what we got. But remember, we rounded. But no, that's actually pretty darn good. That's about what we got, 15.82. Of course, on your calculators, you're going to be putting the data in a different way, but I just kind of wanted to show you that there's all kinds of ways to compute it. You can literally probably find a website that does standard deviation calculations, and it looks like it can look like a spreadsheet, or it can look like some way for you to enter the data values in, and then it'll just compute the standard deviation for you. So again, it's all going to be based on the kind of calculator you're using at the end of the day. Real quick, we're going to use a lowercase s that has a capital for some reason. We're going to use a lowercase s to represent the standard deviation of a sample. The sample standard deviation uses a lowercase s. The population standard deviation uses a sigma, a lowercase sigma from the Greek alphabet. It kind of looks like a cannon or something like that, like a cannon that you'd use. So yeah, there's 2 types of standard deviation. Again, once it's all just something we're putting in our calculator, this becomes just so a lot more boring, if you ask me. So let's do this again. Let's try it for a different set of data, and this one will actually be pretty interesting. We're going to look at 2 different samples. This first sample, the data values are 0, 6, 12, 18, and 24. Okay, that's cool. This second data set, the values are 11, 12, 12, 12, and 13. And these are both samples. So if I'm computing the mean and standard deviation of these samples, I'm not using mu and sigma. Those are for a population. I'm using X bar and S. So X bar and S. And now I'm going to use my calculator du jour, whatever I'm doing. Your calculator can also compute the mean. It'll almost be the same exact procedure as for the standard deviation, and it'll just spit out a couple of different values for you. So let's compute these things. I'll show you how I'm doing it in Excel. So our data values for the first set were 0, 6, 12, 18, 24. There were 5 data values. We'll do the sample mean, sample standard, and so I'll just abbreviate it. There's a couple different things in Excel that does it for you. Again, you'll likely be using your own calculator. Okay, so for this sample of 5 data values, we're getting a mean of 12 and a standard deviation, a sample standard deviation of 9.486833. The truth is that's probably a number that goes on forever and ever and ever and never repeats. So let's just say 12 and 9.49. How does that sound? Everyone cool with that? So we got X bar was 12. S, the sample standard deviation, was 9.49. All right, and I'll leave this writing on the screen when I go back to Excel. Now let's come over here, 11, 12, 12, 12, 13. Let's find the mean and standard deviation of that. So I'll come over here. Let's see what we can do. Okay, so we'll take the average of these 5 data values now. And hey, look, the average is also 12. The sample standard deviation is going to be much smaller. Interesting. So let's see if I can commit these numbers, 9.49.707. I'm gonna have to reproduce these, that's okay. We'll round it to 2 decimal points. So the lesson here is that the means were the same. They had the exact same average value. But look, this data is a lot more spread out. This data is more kind of tight together. They're more clumped together. They'd be very close to one another. So in reality, the standard deviation naturally is going to be much lower because the standard deviation measures how spread out the data is. The mean is just one thing, but the mean doesn't always tell the whole story. Both these data sets had the same average, but we're also interested in knowing how far out the data is. Now, what does 9.49 mean in and of itself? What does that signify? What is that? How do we interpret that? That's a little bit harder to interpret on its face value. But I can at least compare it to a different data set, and I see, oh, well, if this is 9.49 and the other data set is 0.71, this one has much more variability, we call it. It's spread out a lot more. Spread out much more. This data is almost not spread out at all in comparison. So not uber interesting. Lastly, we can talk about the variance for a moment. It turns out the standard deviation is really just the variance. And what I should say is it's the square root of the variance. And so you remember we used sigma without this squared business. We used sigma to represent the population standard deviation, and we use S to represent the sample standard deviation. So the variance is just like one less step than finding the standard deviation. This means that the variance then is found by squaring the standard deviation. That's it. Really just not super interesting. So you have the variance, you want the standard deviation, take the square root of the variance, it'll knock out this squared up here and just give you the standard deviation. You have the standard deviation and you want to get to the variance. Well, you can't square root it, we already went that way. You have to go the opposite way, which is to square it, is to multiply it by itself. So again, not uber profound. And again, we're kind of just sidestepping the standard deviation for the moment. We're going to discuss in a minute what it means. How do we interpret it? How can we use it? So let's say that we have 7 employees in a company. And let's say this is now the population. It's the population. All right, well, give me a hot second, my friends. I'm gonna go put this data into Excel. Let's see, 23, and I'll show you the Excel spreadsheet. 23, no. Let's look at the Excel. Here's the 7 data values. Now what we want to do is we want to compute the standard deviation of a population now. So in Excel, it uses that command with a P instead of an S. If you're on your calculator, it may or may not give you the population standard deviation. It depends on the type of calculator you have. Don't fret because the population standard deviation is almost never going to be something we're interested in. It's just for like this example. So I'm going to take the standard deviation of a population. Okay, cool. So the standard deviation of this population of 7 numbers, where we divide it by 7, is about 11.36. That's the standard deviation, though, 11.36. So sigma, the population standard deviation is that, but what we want is we want the variance here. So we got to compute the square of that. Remember, we rounded. And let's see, 11.36 times itself, basically, 129.05. $129.05. So let me show you that. So it was 11.36 Mafia. That was the population standard deviation. You just got to square it. Yeah, I'm just repeating the calculation because it wasn't showing up properly on Zoom. You get about 129.05. Is that interesting? Not really. I'm just showing it to you. It's very rare that you're going to have to compute the variance. What is the variance? That's even less something that you're going to really get into super detail about. So again, most of this section is done on a calculator. So what we're about to do is interpret the standard deviation. Now we scroll down a little bit. If we have just a sample of these three things, now let's compute the sample variance of these three data, 5, 26, and 36. And now the sample standard deviation was about 15.82, if you'll remember. For just these three data points, the sample standard deviation was about 15.82. But we want the variance. All right, so S, now because it's a sample standard deviation, is about 15.82. S squared, then we take 15.82 and we square it. That'll give us the population, excuse me, the sample variance. 250.27. Again, the variance is just not something we're going to see a lot. So these computations are a bit boring, a little bit dry. So now, let us not talk falsely. Let me go pull up the information for the next part of this section, where we're going to get a little bit more interesting with it, I promise, or I hope. But real quick, let's do attendance. Okay, if you're out there in the Zoomosphere, just type your name in the text box. And I will count you as present. Type out your name. Very good. Boy, sometimes statistics is just a bit dry. There's no, and you know, I like to usually use some jokes, but there's just not really any jokes that I can use here. And I can see it. I can see it in your eyes. If you're here, it's just, this isn't as much fun. Is statistics normally going to be exciting and fun? Yeah. Are you kidding me? Of course it is. Let's see. Am I missing anyone? Viridiana?
Yes, I can't type in. I don't know how to type in my name.
Oh, that's okay. I see you. So you're good to go.
Okay, thank you.
Uh-huh. And then he's here. All right, and then y'all three, Tira, Ryan, Mary Lee. Okay, attendance is completed. Thank you all. All right. So let's get back to it. Attendance is done. Make sure I didn't miss anyone. Nope. So now we're going to get back, and now we're going to actually get into something interesting. So gosh, standard deviation, look, if you want a summary of it, go put it in your calculator. How do you do that? Look for YouTube videos for your specific type of calculator. So all that song and dance was really just for that. Okay. Now what we can talk about is we can talk about what is the interpretation of the standard deviation. And that's where things actually get interesting. That's where it's fun. Now we can actually use the standard deviation instead of just, this is how you put it into Microsoft Excel. And that's boring. That's not as fun. And I'm a fun guy. Well, People say, Josh, how would you rate yourself on the scale of being funny? 1 is you're not funny at all. 10 is you're just knee-slappingly hilarious. And I say, Wilfred, I'm a solid 6. That's just how it is. That's what I am. I'm a 6 out of 10 on the humor scale. He's okay, but you know, he's just not going to go do stand-up comedy. He's not going to entertain anyone with his humor. It's just going to be like, okay, it's good transitory humor. Okay, so the empirical rule is actually really interesting. And there's actually a picture of this. Give me a second. There's actually a picture of this on our page, on our Canvas page for the course. Don't believe me? Shame on you. But also, if you go there, I'll go ahead and show you guys in the Zoomosphere. Ta-da, it's this thing, this business here. This is called basically the empirical rule. This is just a picture of it. And the way it works is that if you have a distribution that's roughly bell-shaped, so if you make a histogram for some data, and it looks like it roughly follows that bell-shaped curve, you know, mine's a little bad here, but I'm not perfect, then approximately 68% of the data will lie within 1 standard deviation of the mean. In other words, if you were talking about a population maybe, whatever the mean value is, if you subtract 1 standard deviation and you add 1 standard deviation to it, about 68% of the data is going to fall between those boundaries. About 95% of the data is going to fall within 2 standard deviations of the mean. So if you subtract off twice the standard deviation, or you add twice the standard deviation onto the mean, bada bing, bada boom, that creates 2 different values. And between those 2 values, about 95% of the data will lie. And finally, virtually 100%, not quite though, of the data will lie within 3 standard deviations of the mean. And of course, we're going to look at examples of this here in just a moment. So that actually creates some pretty interesting ideas, the empirical rule. Remember, you have to have a distribution that's mostly bell-shaped. If your distribution looks like this, let me draw it out. If you have a distribution that looks like I don't know, get funky or weird, you know, there's a clump of data values here, small clumps here, then no, it's just not going to work for that. If it's extremely skewed, you know, or that's a little bit ridiculous, but if it's extremely skewed, something like that, the empirical rule is just not going to apply. What we're going to see is that to be bell-shaped is really strongly related with something called the normal distribution. The normal distribution. But we will handle that in just a moment. So here's a great picture of it. It looks worse than it is. You have the mean, you have the average value right here. If you go 1 standard deviation below or 1 standard deviation above, then a total of 68% of the data falls within that range of values. If you go within 2 standard deviations, 95% falls, 99.7%. So let's do a fun one. That means there's also specific sections. You don't necessarily have to memorize this picture, the specific sections of it. But that means there's some fun things that can come out of this. So let's say for the IQ test. The IQ test, intelligence quotient, it's a test that supposedly determines how smart you are. Of course, that's not really fair, and it's been criticized many times. The data is roughly bell-shaped. It almost looks exactly like a bell-shaped curve. The mean of the IQ test is about 100. On average, people score 100 on it. What does 100 mean? Well, it has its own scale. It's just like the SATs, you know how they're out of 1600 usually, at least for the math and English portion, or the ACT is out of 36. The IQ score is just its own weird scale where 100 is the average, but you can go above 100. So if you're over 100, you're above average intelligence. If you're below 100, you're below average intelligence according to that scale. It also has a standard deviation of 15. And I'm comfortable using mu and sigma here because those are for the population. We're saying the entire population of people on average have an IQ of 100 and a standard deviation of 15. So here's what that's really going to mean for you. This means that on this chart down here, let me scroll it down just a little bit. On this chart down here, we can say the average, the mean, come on. There we go. This thing's being really wonky today. The mean can go right here in the middle, and it's about 100. Now, if we go within one standard deviation, so if you go one standard deviation above, you do 100 plus 15, you're going to be at an IQ of 115. If you go one standard deviation below, you're going to go 100 minus 15, which is 85. So now going even further with it, that means that 68% of all test takers, 68% of all people have an IQ between 85 and 115. That's pretty cool, isn't it? Well, it's moderately cool. It's, yeah, that's what's telling us. This also means 34% of test takers have an IQ between 85 and 100, because 34 is half of the 68%. What else can we do? If you go 2 standard deviations in each direction, if you take the mean of 100 and you add twice the standard deviation, that would give you 130. On the other end, it will give you 70. This says that 95% of people, because of the empirical rule, 95% of people will fall within an IQ of 70 to 130. And then if you go 3 standard deviations in each direction, that will give you 55 down here, and that'll give you 145 up here. That means that virtually the entire population, 99.7% of the population, falls between an IQ of 55 and all the way here to 145. So let's write that out. Let's write that explicitly. 68% of the population falls between 1 standard deviation from the mean, so 85 and 115. So a good chunk, but not quite all of the population falls in that range. 95% of the population falls between 70 and 130. And then finally, almost all, 99.7% of the population falls between 55 and 145. That's what our empirical rule is telling us for these specific numbers over here. Well, that's cool. The cool thing about it is the only thing you really have to memorize is the 68, 95, 99.7% business. Once you have that memorized, you can recreate this chart. So the number of people, or the percent of the population that falls between an IQ of 85 and 100. It's hard, it's being obscured here, but that's 34% of the population. So now you can get even more granular than that. You can zoom in on specific values. Oh, between 70 and 100, well, I needed to say there's at least 13.5% plus this 34% here. So between 70 and 100, there's 13.5 plus 34, that's 47.5. So about 47.5% of the population, almost half of it, falls between an IQ score range of 70 and 100. The number of people that fall between 85 and 145 all the way the heck over here. Well, that'd be 34% plus 34%, which is 68%, plus 13.5%. So that's going to be 81.5%. And then even this sliver here also makes that in. And so 81.5% plus 2.35, 83.85%. I can put that 83.85% fall between, what do we say, 70 and 145 IQ. How did I get that? I added 13.5 plus 34 plus another 34. Now I did do that all in my head, so don't judge me too harshly on that. No, I'm sorry. I wrote that wrong. 83.85% fall between 85 and 145, excuse me. So I only count those slivers between 85 and 145. So yeah, you can do all kinds of things like that. What percent of the population has an IQ above or greater than 145? About 0.15%. That's the amount of the sliver that's to the right of 145. What percent of the population has an IQ that falls below 55? Also 0.15%, because of the symmetry of this bell curve. A small sliver, 2.35% of the population, falls between an IQ of 55 and 70. So there's all kinds of things you can do with that. But if you remember the empirical rule, and you remember, so the 68, 95, 99.7 rule, you can actually recreate this chart. You're just splitting things in half, you're moving things around. It's pretty darn straightforward. Any questions on the empirical rule, either from class or in the Zoomosphere, if you have any questions for me? This would be a good time. So that's actually a really good question. We'll just say yes. Yeah, technically you have to have a large enough sample. So she asked, well, wait a minute, we're using the population values here, mu and sigma. Is that true for a sample? Yes, but it's less interesting when you're just talking about a sample. But we're gonna just say yes for the moment. So you could replace it with X bar and S, and it's the exact same chart. You still have to have the bell curve, but that's actually a really next level question, because that the real answer is, but for our purposes, we'll say yes. It's a gray area, exactly, if you go to the real level. But for our purposes, we'll say yes. We'll keep it simple at the moment. Okay, so let's see if I'm getting any questions out there in the Zoomosphere. Okay. So in the United States, men's heights have a mean of 69.1 inches and a standard deviation of 2.9 inches. The distributions of men's height is bell-shaped. If the distribution wasn't bell-shaped, then you cannot, so okay, we're good. If the distribution wasn't bell-shaped, you can't use that empirical rule. So let's see if without the chart, without that bell-shaped curve graph over there, let's see if we can do this one just knowing the logic behind it. I'll recreate this. You can almost call it the 68, 95, 99.7 rule. In that you can say 68% of the data falls within one standard deviation, 95% within two standard deviations, 99.7 within three standard deviations. So what percentage of men have heights between 66.2 and 72 inches? Okay, that's an interesting question, but wait a minute. These numbers don't just get pulled out of nowhere. 66.2, maybe you can't see it at the moment, but 66.2 is exactly one standard deviation below the mean. So 66.2 is exactly one standard deviation below the mean. Don't believe me? Take the mean 69.1, subtract 1 standard deviation, and you're going to get 66.2. "72 inches falls within is 1 standard deviation above the mean." Don't believe me? Don't believe me? Well, do 69.1 plus 2.9 and you'll get 72. In other words, this is merely asking what percent of men fall within 1 standard deviation of the average height. That's all it's asking. Those numbers equate to being 1 standard deviation below and 1 standard deviation above the mean. Whoops. I guess I just have to reproduce it. So it just wants to know what percent of men fall within 1 standard deviation of the average. We know that the distribution is bell-shaped, so we can use the empirical rule. And which of these 3 numbers does that go with? The 68. Yep. And that's our answer here. Because it's really just asking what percent of men fall within 1 standard deviation. Okay. What percentage of men have heights between 63.3 inches and 74.9 inches? Well, look at this number, look at it closely, see if it's just so many standard deviations from the mean. And it is. If you do 69.1 and you subtract it from the realized value and then divide by the standard deviation. If you do all that, that's telling you how many standard deviations away from the mean it is. And since it's -2, that's telling you it's 2 standard deviations below the mean. So 63.3 is 2 standard deviations below the mean. I'll write that here. Because when we did this computation, we just said how far is it from the mean and divide by the standard deviation, and that's how many standard deviations it is from the mean. If I want to know about the other number, 74.9. If I take the 74.9 and I subtract the mean, then divide by the standard deviation, I'll get +2. And that tells me that 74.9 is 2 standard deviations above the mean because it's now +2. So ultimately, this problem is just asking, at the end of the day, this is ultimately asking what percent of men fall within 2 standard deviations of the average height. So which values from the empirical rule would we use here? 95, exactly, comma windows. So the answer to this one is, well, 95% of men fall between 63.3 inches and 74.9 inches. Exactly. You've deduced it perfectly. Take the value itself, subtract off the mean, and divide by the standard deviation. This tells you how many standard deviations that value is from the mean. And if this comes out negative, it tells you it's that many standard deviations below the mean. If it comes out positive, it's that many standard deviations above the mean. Guess what? That's actually one of our major concepts we're going to talk about. That's called a z-score. We'll discuss what it is in more detail later, but you take the actual realized value, subtract off the mean, and divide by the standard deviation. You compute a z-score. So what a z-score does is it tells you how many standard deviation a given value is from the mean of that data set. And then if it's positive or negative, it tells you which direction from the mean it is. That is something that's going to be very useful here. Let's look at one more quick one. What percentage of men have heights above 72 inches? Well, remember 72 inches, we already did that. 72 inches was one standard deviation above the mean. So what we can do is we can go all the way back to our chart. Oops, sorry. What we can do is we can go all the way back to our chart. And so here was 69.1, the average height. This would have been 72 right here. That's one standard deviation above the mean. And it wants to know what percent of men have a height that is one standard deviation above the mean or more. What percent of men have a height greater than 72 inches? So I would add this one, plus this one, plus this one. Does that make sense? And so add them up, you get 15.85, you can get 16%. Does that sound about right? Yeah, add those three values up. And so that would be our answer here. So about 16% of men have a height above 72 inches. And those are real numbers. Those are actual values for men's heights. Those weren't just made up. So that's pretty cool. Okay, that about wraps it up for today. We finished section 3.2. We did all of it, started and finished it today. So y'all have a great day, have a great weekend, and we'll see you guys here next week on Monday, either in Zoom or in person. Thank y'all.